Right, sorry about the delay. Okay, let's start the class. So welcome to our linear algebra class. So it's a little bit small, right? Give me 1 second. Okay, so yeah, I'll try to find a solution to maximize the screen next time. But let's go ahead with the let's go ahead this time. Okay, so yeah, let me start with my brief intro. So I'm Jae Chu, an assistant professor in computer science department here. And yeah, I did my bachelor in Seoul National University and master and PhD in Georgia Tech in the US. And my research area is machine learning and data mining and deep learning and so on as an applications. So I deal with the computer vision tasks. So if you heard about generative adversarial networks, which is quite popular deep learning techniques in these days, so I heavily work on it, and also I tackle the natural language understanding and generation tasks, such as question answering for dialogue systems and chatbots and so on. And also I do text mining and social media data mining and so on, as well as human-computer interaction and also data and information visualization. Okay, so so this is a basic course information. So we will meet Monday and Wednesday, and on Monday we will have a class from noon until 1:50 p.m. And on Wednesday we have a 15-minute class starting from 1 p.m. until 1:50 p.m. And our classroom is fixed here in this location, and my office is just upstairs in the 5th floor. And so if you want to meet me, then just talk to me after the class, or visit me in my office. And have you accessed or logged into the website called the Blackboard? Has anyone? Okay, so is there anyone who hasn't logged in to? Okay, so the website name is kulms.korea.ac.kr. Okay. So you just log in using the same credential assigned by your school, and then you will access to this course website, and then I post our course slides and also homework to this website. So you can just download these slides from there. Okay, so mainly what we will learn in this class is linear algebra at an undergrad level. So this is basically a math course, okay? But along with the probability and the statistics, this linear algebra is really the key fundamental techniques for many interesting applications or higher level kind of disciplines or literatures. So for example, if you are interested in machine learning or maybe artificial intelligence, this is one of the key course that you have to get familiar with. Okay, and for example, for those students who wants to join my lab, so I asked them to pass my own exam for this specific course of this linear algebra. And so this is that much important to do some higher level or interesting tasks in machine learning and many other applications. Okay, so this is our textbook. So there are several different editions, but I think this is the latest one which we will use in this course. Okay, and for your homework, we will have at least 5 to 6 homeworks throughout the semester, and most of the homeworks will come from the exercise problems, shown in this book. So I will just give the list of the exercise problem numbers in the book. So if you use the previous or older editions of this book, and then those exercise problem will not match, will not be the same. So you might just solve the wrong problem. Okay, so please make sure to have this book as your textbook. And so I believe there is a electronic version of this book. So if you want, you can. I think you can get the file online. Okay, so this is some course schedule. Okay, so this is the grading policy. So homework will occupy about 1/4 of your total grade, and most of these homeworks will be just hands-on solving of these exercise problems. You just solve the math problems by your hand. Okay, and also in the middle of our class, I will ask you to study on your own by using some online lecture about a specific topic, such as this determinant. So what is the determinant? So what's it called in Korean? 네? 고유값? 고유값이라고 했어요? 고유값. 고유값은 이제 뭐 아이겐밸류나 이제 싱귤러 밸류. 네. So the determinant. Its Korean name Korean term is 한별식. So are there any foreign students other than Koreans? Okay, yep. Okay, so what's this determinant in the world of linear algebra, or in the context of a matrix or vectors? So if we are given this matrix, and then determinant of this matrix is defined as AD minus BC, right? What's the role of it? So if it is 0, and then what does that mean? Right. So even if it's 0, it doesn't mean that eigenvalue doesn't exist. I mean, eigenvalue still may exist. Okay, but you're correct. So if AD minus BC is 0, and then it means that this matrix is not invertible, which means that we cannot obtain its inverse matrix. Okay, so we will study heavily on the meaning of this inverse matrix and how to compute it, even for larger matrices such as 3 by 3 or even larger than that. Okay. So for this specific topic of a determinant, I will ask you to study on your own by watching these videos, which is about I think 2.5 hour long video taught by MIT's famous professor on this linear algebra. Okay, and then our class will have 2 exams. One for midterm and the other for final, and then these are the dates, and this is just typical math exam, which is done in a closed book form, and also you will just come to the class to take the exam. Okay, and then if you participate more and more in this class, and then you will have a high chance to get your grade. Yeah, you will get a higher grade. So yes, so the way of this class participation is through just asking as many as questions that you want, and also, yeah, yep, that's it. Yeah. Yeah, and so yeah, oftentimes many students are placed around the borderline, depending on the different letter grade, whether you may get A plus or A0 or A0 or B plus and so on. So this is kind of qualitative criteria. Yeah, depending on how much I remember you, based on your active participation in this class. So yeah, actually, it is often the case that some of the active students may get higher degree of your letter grade at the end. So don't underestimate this factor as well. And for the attendance, yeah, I will not always check the attendance every class, but I just sporadically check the attendance. Okay, but every time you found to miss the class, and then you will, your total point will get deducted by 1/2 point. Okay, so altogether, if we just sum some of these numbers, and then it will have 100%. Okay, but if you miss two classes, and then yeah, you will get 1 percentage point lower than your original grade. And also, let's see. Yeah, and also you will get a higher chance. Okay, higher chance to get called for your attendance checks. Okay, so I may not check all of our students in this class when checking the attendance. I will just check the subset of the students, but those subset will be selected based on your frequency of missed class. Okay, so if you missed more classes, and then you will get a higher chance of getting called in during this attendance check. Okay. Yep. So I have my own algorithm and code, yeah, implemented in MATLAB. So that will just give us the list of the students that I should call to check the attendance. Okay. Any questions so far?
Will this PowerPoint be uploaded on Blackboard?
What's that?
Will this PowerPoint be uploaded on Blackboard?
I think it's already uploaded. Yeah, it's in course materials. Yeah, sub menus. Okay. Any other questions? Okay, and also, let's see. Give me 1 second. So I've been teaching this class for the last 4 years. Yeah, once per year. And then, yeah, it's my actually 5th time. But yeah, I found that it is not always the case that I teach better and better, but I sometimes teach worse than the previous years. But anyways, so this is my YouTube channel, and I mean, yeah, it's yeah, I upload most of my lectures to my YouTube channel, including our classes as well, and also, where is it? Playlist. Yeah. Where is it? Okay. Yes, so 2008 version was uploaded in a different website called KUOCW, which is hosted by Korea University, like online lecture kind of a platform. And also 2017, yeah, here, we see linear algebra lectures as well. So that is exactly the same lecture as this class. Okay, so you can either review. I mean, I will probably upload each lecture that we will have during this semester to this YouTube, and so you can review those lecture videos or these previous ones as well. And also, although it's some small set of lectures, I mean, quite heavily shortened lectures, but there is course taught in Korean as well. Okay, so I will give a list of the links that you can watch later on to review this course. Okay, so there are some shortened but Korean language version of this course. Okay, any other questions? Okay, then so let's start with the chapter 1 called linear equations and also linear systems. So if you haven't brought this lecture slides, then you can just download this lecture slide by going to this KULMS Blackboard website. Okay. Okay, so the first big part that we will study in this course is how to solve linear equations or linear systems or systems of linear equations. So we may not have a good idea about what this systems mean, but this one you can just think of it as a set of linear equations. And then just a simple example of this set of linear equations and solving it is like something like this. Okay, so we have two linear equations, right? And we will see when we can call a particular equation as a linear equation. Okay, but anyways, we see at least two of these equations, right? And what's the meaning of solving this set of an equation? We want to find specific x and y values, right? That satisfies all of the given equations, right? So this is basically the main task that we want to perform in this big chapter of linear equations and linear systems. Okay, and so this is also called systems of linear equations or linear systems. Okay. Okay, and then moving on to the next slide, let's just briefly study this linear equation. Okay, what's the meaning of this linear equation? So here are the inputs or basic settings. So we basically have one or more variables, and in general we can call it as x1 through xn. So it means we have an n different variable. Okay, so in this case we call this guy as x1 and call this guy as an x2, right? So we may have a 3 or more variables, right? So that number of variables is denoted as n, right? So here in this case, n will be 2. Okay, and this is the form of the linear equation that it has to satisfy. So we have those variables, and also for each variable we have some corresponding coefficient as a constant. So these are the given number that is known. Okay, that is known, and also we have some another coefficient or another constant on the right hand side. Okay, so each of these are each of these is a linear equation, and so this guy is the next one, and 2 is a1, and here 1 is a2, right? And this guy is b, right? So this is quite simple. And so this is called a linear equation. And then what is not a linear equation? For example, x squared minus, or so this is not a linear equation because it involves the second order or quadratic term in terms of our variable, right? So this is not a linear equation. And also, this guy is not a linear equation because this guy can be viewed as x1 to the power of 1/2, right? So this is not a linear. But what about this guy? Is this linear equation or not? So this is not a linear equation. Yeah. So this one is not a linear equation because of this term. So this one, is having just a first order term of this of this individual variable of an x1 and x2, but because they are multiplied together, right? When they are added or subtracted, okay? So in that case, that doesn't increase the order of this equation. Yep. So, but in this case, they are multiplied together. So in this case, altogether, the sum of them will be the total order or degree of this equation. Okay. So this is basically the second order equation with respect to x1 and x2. Okay. So in Korean, 네, 이게 그러니까 네, 2차 방정식이기 때문에 그렇죠? 이건 2차 방정식이에요. Yeah, so basically the first order equation is called a linear equation, okay? Which means the maximum degree of a any variable that we have should be at most 1, okay? Okay, and the linear system of linear equations, or in short, linear system is a collection or a set of multiple or one or more linear equations. Okay, but these equations should involve the same or the common set of variables. Okay. Okay, and then what is the solution for this linear system? So the solution is the specific value that of this variable. So for example, in this case, the solution will be this guy. Okay. So if we plug in x and y with the 1, then we can see that each of these equations are satisfied simultaneously. Okay. So that is the meaning of the solution. Let's see. But sometimes this solution of a given linear system, let's think of how many solutions we have in a given linear system. Okay, so in this case, we have, so this is a one particular set of a solution, right? So this is one solution. So in terms of the number of solutions, we have at least, or we have currently one solution. But we can also think of the possibility of having another solution, which means, for example, when x is 2 and y is maybe -1, this one may also satisfy all the equations that are given in our linear system, although this is not the case in this given linear system. But there are there are cases where the linear system has more than one solutions. Okay, and so we have to be careful about the total number of solutions of a given linear system. Okay, so that will work. That will play a really important role in the subsequent or later chapters or later chapters. Okay, so so in this particular case of a linear system, we have only one solution, but there are some other cases. For example, so the first equation. Something like this. Okay, so in this case, it is obvious that we have a solution like this, but also, this guy has another solutions, right? So what's the geometric kind of 네. 요거요? 요거? 네. So that's a good example of a active participation to the class. Okay. Okay, so how we relate the solution of this given linear system with the geometric kind of structure of this equation is that given this equation, we can think of like x2 is represented as this kind of a line, infinite line in the two-dimensional space, right? x1 and x2, right? So in this case, so this is a y-intercept, and then this is an so this is an x y-intercept, and this is an x-intercept. Right, and so the first equation is represented as this line, right? So any point, such as 0, -1/3, or -1/2 and 0, or any other points will all satisfy this equation, right? And what about the second equation? So it will also be represented as another line, right? But if that line, for example, in this case, so in this case, I'll just draw the line hypothetically, but suppose this line is something like this, and the second line is something like this. And then what will be our solution corresponding to this? It will be this point, intersection of it, right? Okay, so but so that way, if two lines are crossing at a particular single point, right, and then that will be our solution to this given linear system. But in this particular case, the first and the second equations will be overlapping entirely, right? So the first and the second line, yeah, will still be the same as this blue line, right? So in that case, still the solution will be any points, yeah, infinitely many points, right? Where any points can lie on this line. Okay. So so in this case, even though we have two equations and also two variables, yeah, we may have infinitely many solutions in terms of the number of possible solutions, right? But intuitively, if this guy is maybe 7, or yeah, so you get the idea about when those two lines are overlapping. So if it is those ratio between each pair of these numbers, 2 to 4, 3 to 6, and -1 to -2, if all ratios are the same as each other, and then it means those lines are overlapping exactly, right? But if those ratios are not the same, at least for one pair, and then it is no longer be a overlapping line, right? So in this case, that line will be something like this. Okay, so we will have a usually one intersection point, right, which correspond to one single number of solutions. Okay. Okay, so yep. So the solution set of a given linear system is the set of all the possible solutions. Okay, not just one single solution, but that solution set should contain or include all the possible solutions. Okay, and also previously we saw two different examples. Whether we have a one single solution or infinitely many solutions. And also there are some other cases where we have no solutions at all, right? So in that case, the intuitive example will be, so we have the same ratio between 2 to 4, 3 and 3 to 6, but -1, 2, maybe -3. So in this case, what does that mean? So if we draw the line of each equation, and then it corresponds to like the case where we have one line over here, and then another line which is parallel, which is parallel to another line. So the two lines are not intersecting or does not meet at any point at all, right? So in that case, it corresponds to have no solutions in this given linear systems. Okay. So at least so far we saw three different cases, although they are very simple. Three cases are like one solution case and no solution or infinitely many solutions. Okay, so we saw these three different cases so far, but are there any other cases where we have, for example, only 2 different solutions or maybe 10 different solutions, which means like more than one, but finite number of solutions of a given linear system. So so there is no such cases, at least for this linear systems. Okay, because as you saw, each of our linear equation is represented as really straight line, right? Really the straight line. So if we consider like multiple straight line, okay, multiple straight line, if the two lines are meeting over here, and then from here and from here, they become closer and closer and met at some particular point, right? But because they are straight, they're really straight line. So once they met at some point, and then they start to move away from each other, right? So because basically this line is not bending, right? So in this case, we may have another intersection that corresponds to another solution, but yeah, by using only the linear equation, which is represented always as a single line, which is really straight, it cannot happen, right? So if we have a multiple solutions, and then that multiple solution, yeah, will only correspond to the case where the two lines are exactly overlapping with each other, right? So we have an infinitely many solution, okay? But it is not possible. I mean, it is impossible that we have a more than one but finite number of solutions, such as 2 solutions or 3 solutions. Yeah, there is no such cases in the world of a linear systems. Any questions so far? Yeah.
Two systems with no solution considered equivalent.
You're considering 2 different linear systems?
If you said like if two systems have the same solutions, that they're considered equivalent. So two systems both had no solutions at all, would that also be considered equivalent?
Okay, so far we only consider one linear system at a time, right? So one linear system is composed of a multiple linear equations, right? And that linear equation, we basically have to find the solutions that satisfy each of our linear equations simultaneously, right? So in terms of that that solution that simultaneously satisfy all the equations, the number of the solutions will be either like no solution or 0 or 1 or infinitely many, right? So far there are only 3 possible cases, right? And then now the next topic or next thing that we want to discuss, yeah, is related to what you asked. So we can now consider these 2 linear systems or 2 or more linear systems. So each linear system is composed of multiple linear equations within it, okay? And this linear system will have its own solution set. And then another linear system will have, its own solution set, right? And if those 2 systems and if their solution sets are exactly the same, and then we call these 2 linear systems are equivalent. Okay, so how about this? 2x1 plus x2 okay, so this is a linear system number 1. Okay, and then let's think of the linear system number 2 as okay, so we are given 2 linear systems, right? And then I just created or I formed those 2 linear systems by having the solution in mind from the beginning. So the first solution, I mean the solution set of the first linear system will be this guy, and the second one will also be this guy. Right? Okay, so if we imagine the corresponding kind of line in the 2-dimensional space for each of these linear equations, so all of them will be different, right? So these 2 lines will be something like, so let's enumerate it. Like this one is 1, 2, and 3, and 4. Okay, so this is the first line, and this is the second line. Okay, so this is the corresponding solution, although, it should be placed over here, right? Okay, I need to So this is the first, this is the second, and this is the first one, and this is 1 and -1. Okay, and the second linear system may have different lines, right? So this one could be third and the fourth line, right? But still, these two linear systems will have the same solution set, right? So in this case, we call these two linear systems are equivalent, okay? Which means that we have exactly the same solution set. But what about this? So are these two linear systems equivalent? So yes, they are equivalent. They are not? Okay, you guys are smart. So what's the reason for not being equivalent between the two? Because this guy, even though this one has this as a one of the solution, right? But from these, in this second linear system, we know that the solution set, I mean the number of solutions is infinitely many, right? Because these two lines are overlapping, right? So in this case, the solution set for the second linear system will not just be this one, but it will be infinitely many solutions. For example, this guy, or yeah, x1 is being 2 and x2 is being 0, right? I think that is another solution, right? So the solution set for the second one and the third, the first one is not exactly the same, right? So in this case, those two linear systems are not equivalent. Okay, and then why do we consider? I mean, what's the main reason that we consider those two linear systems that have the same solution sets or that are equivalent? Yeah, the main reason is because we want to be able to convert one given or initially given linear system that seemed to be quite complicated into a simpler one. Okay, so let me give an example. So this is initially given linear system, right? But what about this? x1 plus 0, x2 is equal to 1, and 0 times x1 . Okay, so this guy and this guy. So let's call this guy as a linear system, for example, 3. So is linear system 1 and 3 equivalent? Are they equivalent? Yes, right? But the third, this third one is really trivial one, right? Because it just gives us the solution directly, right? But still, it can be viewed as one particular example of another linear system, right? But this is equivalent to the first, the initial one that we are given, right? So in the latter part, we will mainly study how to convert initial linear system into a simpler form that will just directly or naturally reveal the solution. Okay, because this one is really the easiest form that will directly reveal the final solution, right? So we will study how to convert or transform this guy into another linear system, but still the assumption that we have to maintain throughout this process is that once we obtain or once we transform one linear system into another, and then those two should have the same solution set or they should be equivalent, so that the latter one or the resulting linear system will just give us the same solution for the initial linear system. Okay. Any questions so far? Okay. So as I mentioned, the linear system, the system of linear equations is the same as linear system. So this is a like abbreviated name for this system of linear equations. So we studied there exists only 3 different cases: no solution, only one solution, or infinitely many solutions. Okay, and in the case of no solution for our given linear system, and then in that case, this linear system is called inconsistent, which means for this no solution case, we call this a linear system as inconsistent. And for these 2 other cases where we have at least one solution, whether it is a unique or single or infinitely many solutions, at least we have solutions, right? So in that case, we call it as consistent linear system. So what's the meaning of this word in Korean? 이거 뭐 consistent가 무슨 뜻이죠? 네? 뭐 일관되다 뭐 이런 거죠. 그 사람은 참 뭔가 좀 일관돼. 그러면 뭐 he's a quite consistent guy 뭐 이렇게 할 수도 있죠. 뭐 어쨌든 그래서 consistent라는 말은 이제 여러 개의 이퀘이션들이 이제 뭔가 그래도 적어도 동시에 만족하는 케이스가 있다. 그래서 이제 일관되게 뭔가 모든 어떤 주어진 이퀘이션 혹은 조건들을 다 만족하는 어떤 일관된 하나의 케이스가 적어도 하나의 케이스가 있다는 뜻이고, inconsistent는 그런 이제 뭔가 일관된 혹은 하나의 어떤 특정한 솔루션이나 x1, x2 그런 값들이 이제 모든 애들을 다 일관되게 만족시킬 수는 없다. 그래서 이제 얘들이 좀 일관되지 않다. So yeah, no solution makes our linear equations inconsistent in terms of their individual solutions. Any other questions so far? Okay, so this is the first class. So yeah, usually I will have a 10 minute break from 12:50 to 1 p.m. from the next week. Okay, but this week or today, I will have maybe 15 to 20 more minutes and then just end our class today. Okay, so okay, and then now let's move on to the matrix representation or notation of our linear system. So let's think of this given linear system where we have 3 variables, x1 and x2 and x3, and 3 equations, right? And then we can just build up something called a coefficient matrix, where we just bring those numbers. So we have 1 here, and those numbers are placed as the first row and the second row, right? We just bring or extract those coefficients from multiple equations and then form this a single matrix. Okay, so that is called coefficient matrix. Okay, and then there is another matrix that we can build from this given linear system, which is called augmented matrix. So augmented matrix is just a 1 column augmented version from this coefficient matrix. So we understand the coefficient matrix, but how about this part? 0 and 8 and -9, which is constant value on the right hand side. Okay, so we just bring that in to the 4th column or the last column to form our augmented matrix. Okay, so this is just a term, but we will heavily use this coefficient and also augmented matrices in your maybe exercise or homework problems. Okay, and then once we consider this coefficient and augmented matrix, and then yeah, instead of being given the linear systems or the set of linear equations, let's suppose we are just given the coefficient matrix. Okay, for example, like this matrix, and so suppose this one is coefficient matrix. Okay, so without being given the linear system, but we are just given this coefficient matrix, and then we can easily say how many equations we have and how many variables we have, right? So how many variables do we have here? 4, and also the number of equations, 3, right? But what about what if this guy is an augmented matrix? So in the case of an augmented matrix, this guy is the constant part on the right hand side. So in this case, three variables and 3 unknowns, right? Okay. And then now I believe you guys are familiar with the rows and the columns of a matrix, right? So yeah, just apart from, I mean, let's just forget about this linear systems, but let's just think of just matrix like 1, 2, 3, 4, 5, 6. Okay, so here we have this horizontal vector, or horizontal kind of a one-dimensional set of or list of values. So that one-dimensional kind of list of numbers are called a vector, right? And also if it is a two-dimensional array of the numbers, and then we call it as matrix, right? And then how about like three-dimensional array of numbers? So what's it called? Does anyone know? So yeah, so for example, 1, 2, 3. So this is only like one-dimensional array, and this is like two-dimensional array. So one-dimensional array is called a vector, and two-dimensional array is called a matrix. And what about the three-dimensional array, such as like 7, 8, 9, and maybe 10, 11, 12, right? And so in that case, we have this kind of shape, right? Although it is not aligned well, but we can think of this as a three-dimensional array, right? So what's it called? So this is called a tensor, or yeah, in general, 3 or higher dimensional array is called a tensor. And so, have you so does do you guys does it remind you of anything? TensorFlow, right? So in the Google's deep learning library called the TensorFlow. So in the case of TensorFlow, yeah, basically tensor is flowing. So this kind of tensor, which is a 3 or more dimensional array, is kind of flowing through our deep neural network layers. Okay. Okay, this is a kind of side story or side thing that we are talking about apart from the core linear algebra, but let me see if we can. Yeah, although the resolution is a little bit low, but so this is one example of a deep learning architecture called a VGGNet that is quite widely used for image classification. So what is the image classification? So given an image, so we want to classify whether this image is a cat or dog or person or maybe desk or laptop and so on. And also in the case of facial recognition, which is just another image recognition task, this is just identifying or classifying. I mean, given a person's image, it is determining whether this image is belonging to maybe John and David and James and Jane and so on. Okay. Okay. So in the case of deep learning or deep neural networks, so basically this tensor or a multidimensional array is flowing. Okay. So in the case of the initial image that we are given, suppose that image is like 224 by 224 as a horizon, basically the resolution of our image. And also, this is already a tensor because if we look at the given initial image in a colored form, and then it will have RGB, like 3 different channels, right? So in that case, we can already think of 224 by 224 by 3, right? At each pixel, we have 3 different values corresponding to red and green and blue channels, right? So it is already a tensor. And then, in general, this deep neural networks is actually transforming it into another one, for example, 112 by 112 by 128. So it means, the first 2 numbers are width and height, and the third number is called the depth or channel. And so we have initially 3 channels corresponding to RGB, and we have initially the spatial resolution of 224 by 224, but once we pass through a few initial or first layers of a given neural net, and then our tensor or 3-dimensional array has been transformed into 112 by 112, which is like a 1/2 reduced version of our original image, right? But at the same time, or on the other hand, the depth was increased from initial 3 channels upon RGB into 128 different channels, right? And then what does that mean? I mean, what's the meaning of each of these 128 channels? We have an idea about the red, green, and blue channels. I mean, if that particular pixel is more and more red, and then we will have a higher and higher value corresponding to that red channel, right? But in the case of this 128 different channels, each channel is corresponding to a little bit of a semantically meaningful notion, such as given this image, so this is 121, 112, right? And then we have an increased channel of 128 channel. But what about the first channel and the second channel and the third channel? What's the meaning of it? The first channel is, for example, the degree of how likely or how much this pixel is corresponding to a dog, for example. Okay, so this is the dog channel. Okay, analogous to like the degree of red channel. So this is dog channel. So how much this pixel is belonging to a dog. Okay, so if we have maybe dog here. Okay. Okay, so this one is not clearly not belonging to dog, right? So in that case, this channel will have really small value. But what about the pixel corresponding to this part, or maybe this part, or this part, because they are belonging to the dog-like shape or dog's body or face? So in that case, the first channel value will have really high value, right? Okay, so basically, this is we can see that this tensor structure or tensor array is actually flowing through each of our layer in the deep neural networks. Okay, so that's the meaning of this tensor flow, because tensor flowing is playing a role of transforming the given tensor into another output tensor. Okay, so yeah, back to the matrix case. Let me rewrite it. So in terms of vectors that is included in this matrix, we can think of these two vectors, 1, 2, 3, and 4, 5, 6 separately as two different vectors, right? But these two vectors are in the form of a horizontal vector, right? So horizontal vector is called row or row vector, and we also have another vector, another set of vectors that can be extracted from this vertical kind of vector. Each of these vertical vectors. So each of these vertical vector is called column. Okay. So in this case, how many rows do we have in this matrix, and how many columns do we have? 2 rows, 3 columns, right? So we call the matrix the size of this matrix as 2 by 3. Okay. This is corresponding to the number of rows. And this is corresponding to the number of columns. Okay. So when I studied linear algebra in my undergrad, so I didn't do very well. I only got maybe B0 or B+. So I didn't study very hard. Even after I complete this course in my own semester in the undergrad years, and I was still confused about which one is row and which one is column. Okay, so let me show how not to get confused. So what's the meaning of this column? I mean, not just mathematically, but in general. So as we can see, the meaning of this column is, in Korean, 이게 뭐 기둥이라는 뜻이죠. So this column should be constructed or built vertically, right? So that way, column is a vertical vector. Okay, but when talking about regarding the size of a matrix, we always represent the number of rows first, and then the number of columns. Okay, so this is 2 by 3 matrices. Okay. Okay, so given this m by n matrix, so if it is a coefficient matrix, how many variables do we have? N or m? M? N? Again, how many variables do we have? M or n? Yeah. So if m is 2 and n is 3, then something like this, right? So we have a 3 variable, right, and 2 equations, right? So this is the number of equations, right? So this is the number of variables. Okay. Okay, and then let's briefly discuss how to solve this linear system. So we want to be able to solve or obtain the solution for a given linear system. Okay, and then our main strategy is, as I mentioned, we basically transform this given linear system into another equivalent linear system that maintains the same solution set. Okay, so eventually, or intuitively, we want to change or convert this complicated linear system into this really simple linear system. Okay, how do we do so? So there are several different methods that we already studied in our middle school, I think, right? So what was the name in Korean about the way of solving linear system? 네, 뭐 그런 거 있었죠. 소곱법. 또 가감법. 대입법. 또 있었나요, 뭐가? 네? 뭐라고요? 오케이. 근데 가감법과 대입법은 아는데 소거법은 뭐죠? 똑같은 건가요? Okay. Okay, so among several different ways of solving linear systems, what we will focus on this class is this guy, 가감법. So this one works in this as follows. So if we have if we have this kind of equation, and then what's the way of doing 가감법? So we basically let's just remove this variable by using the first equation. Okay, and in this case, we can So there are several different, many different ways. So for example, let's just multiply this by 2. Okay, 2x2 is equal to 0, and then we just subtract from this guy and this guy, and then negative x 3 times x2 is equal to 3, right? And then once we obtained x2 as negative 1, and then we can just either plug this in to previous equations to obtain other remaining variables, right? So this is how to apply this 가감법. But how about this? Instead of just multiplying the second equation by 2, how about just multiplying the first equation by 1/2 and then subtract it? So that would be the same thing, right? But there are several other ways. How about just trying to remove the second variable first? Okay, let's just eliminate the second variable first. And in this case, we can just add them together because those two coefficients are matching with the negative signs. And then we just add them together, and then we can first obtain x1, right? So there are many different ways of applying this 가감법 to solve this set of equations. But what if we have many equations and many variables? So there could be many different ways of applying this 가감법, right? But it's not very systematic. Or let's imagine. So as our today's homework, I will just suppose I just ask you to. It's not on homework, so so if you are given on homework where you have to implement this 가감법 for any given linear systems, where you have maybe 3 or 5 or 7 equations or variables, and then how can you write your own kind of systematic algorithms, right? So building up that algorithms and studying this systematic way of solving this linear system is the main part that we will study in this chapter and the 2 or 3 later chapters as well. So our rule, as our consistent rule, is as follows. So let's just represent this linear system into augmented matrix, for example. Okay, and then we use the first equation as our eraser. Okay, eraser, and then which variable to erase? We always start with the first variable. So this will work as an eraser, and then the remaining equations will be the ones where we erase the variable. And which variable to erase? We always erase the first variable first. Okay, so what that means is by using this variable, we erase this guy and this guy. Okay, by using 가감법. And how we do it? Is as follows. The first one, the second equation is already erased variable for the first one, right? So we have nothing to do. But how about this guy? How can we erase this guy? We always erase by multiplying our eraser equation, which is always the first equation, by some scalar. So in the case of -4, and then we have 1, and then if we multiply -4 and then add it to the third equation, okay, and then something like this. Okay, it's still 0, and then we add it to the last equation, and then we replace that simplified equation. We replace the last equation with that simplified equation. So once this guy is erased for this guy, and then we just add it to the third equation, and then it's -3 right? Okay, and then this guy will replace this guy. Okay. Okay, so let's now think of the equivalent linear system. Our new transformed equivalent linear system is composed of this guy and this guy and this guy instead of the third guy. Okay, so this guy, and this guy, the set of these three linear systems will maintain or have the same same solution as the initial linear system, right? Okay, so in the case of a representation of this augmented matrix, we can represent that as an augmented matrix, right? And then what's the next step? Okay, what's the next step? So intuitively, by using this guy, we erased these two, right? And then, okay, so let me give another example. So what if we had like 2x1 plus 2x2 and minus 8x3 is equal to 8. So in that case, if it will be 2, right? It will be 2, and so this one should be erased as well. So in that case, how can we erase it? So the first one times 2. Okay, this time we multiplied this eraser equation by 2, and then -2, right? And then added it to the second equation, right? And then we have to just multiply this eraser by -2, and then we add it, and then this guy will be added to form 6 and -10, right? And then similar to replacing the last equation with the newer equation, we also replace the second equation by a newer equation with the one variable eliminated. Okay, so once we used this variable and this first equation as eraser, and then what we basically do is to erase this variable from all the remaining equations. Okay, and then let's think of the matrix kind of a shape in terms of where we find the 0. So the first equation was an eraser, right? That was temporarily multiplied by a certain scalar and then added to the subsequent or each of the remaining equations, and then those remaining equations were replaced by a new equation, right? But still, once we completed this process, and then this guy was our eraser. And then what about this part? All the coefficients in the subsequent equations will have 0 coefficient for that erased variable, right? Does it make sense? Okay, and then now it's time to design our recursive algorithm. If we imagine like how to program or implement this linear system solving algorithm. Okay, and then now this one worked as an eraser in the previous stage, and then we now move on to this part. Okay, So we just focus on that part because this part will always be 0, right? And then now we have, you can think of this situation as having the smaller linear system where we have one less equation and also one less variable because we removed all the first for the first variable. Okay, and then now focusing on this part, out of 3 equations, we now have 2 equations, but out of 3 variables, but also we have only 2 variables. And then we do the same thing. Okay, we now use this guy as our eraser, and then which variable to erase? By using this guy, we erase this guy. Okay. Okay, and then let's imagine the next process will be something like this. So the first one, and then we have 0, and then the second one, using this, we erase this guy, right? And so we now have the smaller one, right? So at some point, we only have one variable and one equation, which will just give us the direct, easy way, easy solution for that single variable. And then we can just plug this guy into upper equations, right? So that's how we solve this linear systems. Okay, so this is at least the systematic way that we study much in this class. But I think the time has more time than I expected was spent. So let's wrap it up today. So we will continue how to continue this process to further steps. Okay, so that's it for today, and then we will meet this Wednesday at 1 p.m. in this classroom. Okay, thank you very much. 네.
질문이 있었는데 여기서 만약에 영역 불응식 그런 것처럼 만약에 x1이 0보다 클 때는 x1 이퀄 x2인데 x1이 0보다 작을 때는 x1 이퀄 마이너스 x2라든가 그런 식으로 되면 두 개의 솔루션이 나올 수 있게 되는데 그럼 영역은 리니어로 안 치는 거고
네, 그건 리니어로 안 쳐요.
그리고 또 그 솔루션이 없는 두 시스템은 이퀄블렌트한 건가요?
아, 네.
0과 0이 지금 널널
네, 좋은 질문인데요. 네, 이퀄밸런트해요. 솔루션이 없는 어떤 리니어 시스템이든 어쨌거나 아까 정의상으로는 솔루션 셋이 정말 같으면 두 개의 리니어 시스템이 이퀄밸런트하다고 했으니까 네, 맞아요.
다름이 아니라 그 1학번 저번에 예전에 이메일 보내가지고 이제 수강 한다고 말씀드렸었는데 저희가 학지부에 전화해보니까 학지부에서 말하기로는 이게 이제 1학년 강의이고 이제 4학년이라면 마지막 학기니까 직접 넣어준 3학년의 경우에는 이제 수강 신청으로 신청을 이제 그 특정 몇 자리에 저희가 해야 되는데 만약 그때 정정에 저희가 시도는 하겠지만 안 된다면 따로 어떻게 신청이 가능하실까요?
네, 거의